So this is actually x squared, however you want to write it, x squared plus y squared minus 1 divided by x minus 1 quantity squared plus y squared. Alright, so then what? Well, now you got your u, right? And you got your v. So to solve Laplace's equation on the exterior of the unit circle, subject to the boundary conditions, you know, A and B, as illustrated, I just take this u and this v and just, you know, it's to, if you'll allow me to avoid some. So basically, you have just phi is equal to, let's see here, I'll do the 10/20 one. So you like 10 plus 20 over pi, and then we'll use the inverse cosine again. Cosine inverse of what? Of u. Well, I'll just write it this way: u over square root of. I mean, okay. Well, you see, it's quite awful where that and this go up in here.
Sounds like Mathematica.
Yeah.
Isn't that beautiful? And that allows us to solve Laplace's equation outside the disk with whatever boundary conditions you like.
So with that, you can take, if you can find a function that will map, like whatever your function is, if you can find the mapping, then you can just do that and plug it in, and it solves it.
Right, and that's not the only, like I'm showing you this argument as sort of a template, you know? The template here's the argument. I showed you guys last time that we can build an annulus as our template, and then you can map that annulus, map to that annulus from other things. The more complex functions you know, the more you can do. For example, I could take a 0 to 45 degree wedge, and I could use the fourth power function. Right? In fact,
map it to G as well.
Yeah. So you could basically take any sector you want in the z-plane, and you can solve Laplace's equation on the sector with constant boundary conditions using this template solution in the conformal mapping technique, the way we've sketched here. But there are.
PM.
It's very interesting.
There's more you can do, you see, because, I mean, the thing is, to fully appreciate the technique, you have to appreciate the full templates. I mean, like, so in here, I think, yeah, he solves his theorem 10.2, right, is the n-value Dirichlet problem for the upper half plane, where basically he shows you how to find solutions. So he's got these points of discontinuity, whatever constant you want here, 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 just different constants every so often. And so if you can solve that, right, then you can find conformal mappings which map that half plane to other things where, you know,
Do they have to be periodic points or just like any, like 1, 7, 23?
These don't have to be periodic, I think, no.
Okay.
These are just separate points and constants, and it's just a proper sum of inverse. If you look at actually what the solution is, it's just a sum of properly weighted arctangents.
To that half plane.
And then you could do something like map it to stuff like this. You could find the right conformal mapping, yeah. So anyway, that's the basic idea. The math behind it really, like the driving force is what I showed you last time. It's just this extra little composition of functions idea. Surprisingly, I think it's really staggering to me the kind of things you can do with this. I don't know. I just it always impresses me when I actually do an example. But
I remembered.
Oh, I was just seeing if I was over an hour. I had hoped that I would only have one video to post, but I see I have talked too long. Okay, so getting back to your research problem. first thing you have to do is find a nice template solution that you like. Right? Something like sort of analog to the half-plane solution or whatever. And then you want to find some hyperbolic functions and see how they behave. Like, what do they map? What is the geometry of hyperbolic mapping? What does the hyperbolic map do to various shapes in the hyperbolic plane, right? And I think we're getting closer to explaining what your problem is, but I haven't quite pinned it down yet. But you have a sense of what I'm
Right.
saying.
It seems like the thought is to kind of see how much of this we can do with only hyperbolic numbers. Is that kind of the general idea?
This is, yeah, basically. I mean, this is still going to be the case. If I've got a hyperbolic function, right, and if I have a hyperbolic function which solves the wave equation on some particular domain, right, and if I have another hyperbolic function which maps to that domain, then the composition of the solution to the wave equation and the conformal mapping function is also going to be a solution to the wave equation on whatever domain takes your template domain as a target.
Mm-hmm.
Like, none of this, those ideas are not unique to complex. Those are just mapping ideas. The thing that's uniquely complex is the fact that the component equations to the complex function satisfy Laplace's equation. And like the larger program of my research is finding algebras which take different partial differential equations as their Laplace equations. It's part of what I'm interested in. It's an old problem. So the question is, what for a given partial differential equation, what is the function theory which takes it as its Laplace equation?
Kind of interesting.
Anyway, thanks guys. I really shouldn't put these things on YouTube. People might copy it.